Right. Hello, guys. Nice to meet you again. So this will be our third lecture on the dot product. In comparison to the previous two lectures, 12.1 and 12.2, this is more conceptual. So the previous two is more on a introductory basis, but in this section, we will be starting on some important theorem and important formulas. So make sure you get tuned on and really focus on what we're going to do today. Okay, so first of all, let us define what is a dot product. So a dot product is an operation between vectors. Given a vector u, represented by u1, u2, u3, v represented by v1, v2, v3, then the dot product between those two vectors, h by u and v, my bad, there's a typo here. The dot product between the two vectors, u and v, is given by u dot v. And the outcome is a scalar, meaning it is a just number instead of a vector. So it is u1 v1 plus u2 v2 plus u3 v3. So what you're doing in the dot product is basically multiply the entries entry-wisely, u1 u2, u1 v1, u2 v2, and u3 v3. And then you get a scalar. Okay. The same thing works for two-dimensional space. So let's see some examples. So first of all, I want you to find the dot product between 2, 1 and minus 3, 4. So let us try to do that. Let me just copy it. So 2, 1 dot product with minus 3, 4 is simply you multiply everything entry-wisely, 2 times 3 plus 1 times 4. Okay. Then you get minus 6 plus 2, sorry, plus 4, so that's 2. So the dot product between these two vectors, this two-dimensional vector, is 2. Secondly, we're dealing with a three-dimensional vector. Do the exact same thing. We multiply the entries together. So 4 multiplied by 1 plus minus 3 multiplied by root 2 plus 2 root 2 multiplied by minus 3. Okay, so minus 3. Right. So that should give you 4 minus minus 3, sorry. Minus 3 minus 6, so that's minus 9 root 2. Okay. And similarly, for our last example, it is again a three-dimensional inner product. So if you take that inner product, you will get 1 times 6 plus 2 times minus 1 plus minus 4 times 1. And that'll be 0. Okay. So that's the definition for inner product. Sorry, for dot product. There are different names for this dot product, and I just accidentally called it inner product, which is also a name, but that means to be consistent, it is called dot product. So we see that dot product is simply you multiply the entries entry-wisely, so u1 v1, u2 v2, u3 v3, and then add those up. So a dot product is an operation between two vectors, which gives you a scalar, right? Okay, so after we introduce the operation, it's natural to introduce the properties of that operation. In this case, you have a natural commutating feature. So u dot v is equal to v dot u. Obviously, this is because u1 v1 is equal to v1 u1, right? So u dot v is always equal to v dot u. And also there is some distributional law. U dot v plus w will be u dot v plus u dot w. Okay, this is a vector addition. So if you add the vector up first and then you take the dot product, it'll be same as if you take the dot product first and then you do the vector addition. For the third property, the dot product is respectful for the scalar multiplication. So if you take the dot product between u and v, this becomes a scalar, right? So a times that is basically just not a number times a number. So that there is no scalar multiplication involved. It is just number times number. It'll be the same as au dot v. So au here is the scalar multiplication of u. So if you do the scalar multiplication first, and then you do the inner product, the dot product later, then you get the same thing as this. And the same thing is for if you do the scalar multiplication on V first. And that is also quite intuitive because basically when you're doing scalar multiplication, you simply multiply each entry by A, right? So whatever you do first, you always get this number, correct? And then we have a natural law, which is zero vector. So let us recall, in 2D, this is this. In 3D, this is this, okay? So 0 dot V is always 0, which is natural because 0 times everything is 0. And the last, which is kind of important, is that if you dot product a vector towards itself, then you will get the magnitude of that vector squared. So let us recall what is the magnitude of the vector. It is the sum of the square of entries. And then you take square root, right? That is the length or the magnitude of the vector. So 1 to 4 is quite obvious. 5 is also obvious, but let us do the computation here. So we see that V dot V by definition is V1, V2, V3 dot V1, V2, V3, right? And by definition, it'll become V1 squared plus V2 squared plus V3 squared. And again, by definition, this guy is the magnitude of V, right? So this guy is the magnitude of V squared, okay? So keep this in mind. The dot product between the same vector gives you the magnitude of that vector. This is an important feature for dot product. So that is kind of summarize what we have done now. We have done learning 3 operations about vectors, which we will learn the 4th in the next lecture. But the first feature is vector addition. So you add 2 vector and then you get another vector, right? And the addition is entry-wise. So the first entry of u plus v is u1 plus v1. And the same for the rest of the entry. The second operation we learned is scalar multiplication, which is also quite intuitive. If you multiply a vector by a constant c, then you get cb1, cb2, cb3. So the output is still a vector. Yeah. Last, we learned the dot product today. This is an operation between 2 vectors. You're trying to multiply 2 vectors in some sense, and outcome will be a scalar. It's not a vector, okay? After doing a dot product, we get a scalar. So for instance, listing does not make sense. If you're trying to multiply, if you're trying to take inner product, take dot product between 2 vectors, and then you take another dot product between this thing and that thing, it's not well defined because this is a scalar and this is a vector. So at most, you can say that this is a scalar multiplication, right? But you cannot do dot product between a vector and a scalar, right? Okay, make sure you're aware of like what is the input and what is the output of these operations. Now, why do we introduce this string notation? Why do we want to define the multiplication to some degree of the vector by this string formula? That's because there is some nice geometrical interpretation. So let us do this first big theorem. So whenever I use a red bracket, it's quite important, and I encourage you to memorize like what we're doing here because it'll be a important milestone for our work to build on. So if theta, this is a Greek letter, it's called theta. We usually use that to represent angles. We also use like alpha and beta to represent angle. In this case, it is theta. So if theta is an angle between u and v, then u dot v, the dot product, will be the magnitude of u times the magnitude of v times cosine theta. I hope you guys are familiar with trigonometric functions. So this is cosine theta. So let us first define what is the angle between u and v, to be precise. So angle between 2 vectors is defined to be an angle formed by joining the starting point of the vector. So if this is a vector pointing this way, and if this is a vector pointing this way, then we have to join the starting point first, and that is the angle that we are interested in. So in diagram, this will be theta, okay? You do not do something like this. This is not the angle. You have to move it here, and this will be the angle of interest, okay? And usually we choose the angle between 0 and 180, but there is no standard way to say this, but because anything can be restricted to between 0 and 180, right? For example, if you're considering this angle, then you can just speak of this angle, right? say this is 300 degree, then it is sort of equivalent to 60 degree, right? Because knowing one knows another. So let us just restrict ourselves to 0 to 180. Okay, so now let's restate this theorem because this is very, very important. So a geometrical interpretation of this algebraic definition of dot product can be represented by this. U dot V will be the length of U times the length of V times cosine theta, where theta is the angle between U and V, defined as what we just said. Okay, so let's prove this, and let's go through the details. So if you draw U, if you draw V, then geometrically you can interpret this vector as U minus V, right? One way to see this is that V plus U minus V gives you U, right? They have the same starting point and ending point. So this will be U minus V, not V minus U. V minus U is this direction, okay? Although they share the same net, but they have different directions. So according to law of cosine, make sure you're familiar with like law of sine, law of cosine. Those are basic geometric objects we might or might not use in our future course. So law of cosine states that, let me recall that really fast. Say this angle is called A. Then you could represent A in terms of B squared plus C squared minus 2BC cosine A. So it is sort of a extension of Pythagorean theorem. Whenever A, the angle, is 90 degree or not, you always represent the side A, like this formula. In a particular case where the angle A is 90 degree, cosine A becomes 0. And this reduced to our usual Pythagorean, right? So this is called a law of cosine. So if I apply law of cosine to this angle theta, then the magnitude of U minus V squared, the A squared we just mentioned, will be B squared plus C squared minus 2BC, 2BC, and cosine theta, right? So that's the definition. Okay, now how do we proceed? So we've seen in the previous proposition that for any vector, the dot product between two vectors will be its magnitude squared. So in this case, U minus V squared will be U minus V dot U minus V. Be careful, this is the dot product, that is scalar product, okay? It is a operation between vector and vector. And as we mentioned again before in the proposition, we know that you can distribute everything. So U minus V dot U minus V will be U dot U, which again gives you the magnitude of U squared. U dot minus V gives you minus U dot V. Minus V dot U gives you minus V dot U, and V dot V gives you V squared. Okay, so this is just a simple folding. And again, by symmetry, by the commutation property of dot product, U dot V is same as V dot U. So one thing you can see here is that nicely in this equality, we can actually cancel out U squared, V squared, and V squared. So on the left-hand side, you're left with minus 2 UV cosine theta. To be precise, minus 2 magnitude of U, magnitude of V cosine theta. So that's this. And on the right-hand side, these two guys are the same, right? So it is minus 2 U dot V. Okay. So now you can cancel out the minus 2, and you get U dot V is equal to this guy, which is what we want to prove, right? Okay, so that's how we prove the formula. Basically, it is depending on the law of cosine, but the takeaway is that the dot product between two vectors is always equal to the magnitude of that vector multiplied by the magnitude of another vector multiplied by cosine theta, where theta is the angle between those two vectors. Okay. In particular, a really nice application about this formula is to state it reversely. What do I mean? So if you divide this thing here, then you'll get that whenever theta is the angle between U and V, then cosine theta will be U dot V divided by the magnitude of U times the magnitude of V. Okay, so let us recall this once again. This is a scalar, okay, that's a number. So everything here is a number. You get a cosine as a number, so you figure out the angle, right? So what this theorem tells you is that throughout pure algebraic computation, we know that this by definition of the algebraic definition, right? So U1 V1 plus U2 V2 plus U3 V3, and those are also defined purely algebraic. You can compute the magnitude of a vector through squaring each entry and taking square root, right? So through all those algebraic operation, you can get the cosine value for the angle that we desire, right? Again, let's do some examples to practice what we just learned. So first of all, the first problem is asking you if the length of U is 1, the length of V is 2, and the angle between them is pi over 6, then what is the dot product? So let us just apply the formula, right? For the first problem, you have U dot V by definition is the sky. Let me just copy that. The length multiplied together, and then you multiply the cosine value of the angle. So make sure you familiarize yourself with this trig function thing. We know that 6 over pi, sorry, pi over 6 is 30 degrees, right? So cosine of that will be, let me write it, okay, here we go. This will be root 3 over 2, right? So that will be 1 times 2 times root 3 over 2, which in particular should be root 3 over 2. Root 3, sorry. And that's the inner product between, the dot product between U and V. Now, secondly, we're asked that U and V are given by that, and what is theta? So we know that in a reverse way of stating the law I've just sent you guys, cosine theta will be defined to be, actually evaluated to be U dot V and the multiplication between these two guys, which is just 3 times 1 plus 1 times minus 2 plus 2 times 1, right? And in the denominator, you have the length. Let us do this by mind. So you have 3 squared plus 1 squared plus 2 squared, right? So that's 4 plus 1 plus 9. That's 14. And for this guy, you have 1 squared plus 4 plus 1. And that's square root of 6, right? Okay. And in above, you get 3 minus 2 plus 2. So that's 3. So eventually, you can get something like this. Like that. Okay. And now take our calculator and you try to take the inverse. This number. And this is approximately, let me see what I do. Where is it here? So it should be around 70.89. Let me just write this. Okay. Make sure that you guys know how to use the inverse trigonometric function in your calculator. And I'm still considering if I want to make a video about how to convert your output as a inverse trig function. Because, for example, the output for sine value will be within minus 90 to 90. But in general, we want something, say, between 0 to 180 would be better. So you can convert that by like maybe adding 180. But for cosine, it's quite simple because the inverse, the range of the inverse cosine will be within 0 to 180. So what inverse cosine gives you exactly what we want. So in this case, there's no any adjustment need to be made. Okay. So do the cosine thingy, find the cosine via the product, and then take the inverse cosine. You'll get your desired angle. Okay. There's no ambiguity about that. Okay. So now we can interpret the dot product using a geometrical feature. So if you're given two vectors, u and v, and they form an angle like this, I don't know why I forgot to write down the vectors here. So u and v. So if uh if the angle between those two vectors are acute, that means that u dot v will be positive, right? Because an acute angle gives you a positive value of cosine. So that is positive. And if they're perpendicular, meaning that theta is 90 degrees, cosine 90 is 0. So u dot v will be 0. Lastly, u dot v will be negative whenever you have an obtuse angle between those two angles, those two vectors, okay? Usually we use a more fancy term for perpendicular, which is orthogonal, okay? So we call two vectors to be orthogonal if their dot product is 0. So now we have a nice algebraic feature about the dot product. You know the definition. We also have a nice geometric feature. The signature of the dot product represents exactly whether the angle between the vectors are acute, right, or obtuse. Okay, so there's that. Now let us do the exercise. So we want to find a unit vector that is orthogonal to I plus j and I plus k. So recall the definition of center basis ijk from our last video. I is 1, 0, 0, j is 0, 1, 0, I is k is 0, 0, okay, in a 3D space. So now we know by definition, if you want to find out whether a vector is orthogonal to another vector, then you want to find inner product, right? So let us first assume that v equals to, let me use x, y, z to represent the variables. So first of all, we know that this is perpendicular or orthogonal to I plus j. Where I plus j is just 1, 1, 0, right? You have 1 in the x coordinate, 1 in the y coordinate, and 0 in the z coordinate. So you get x plus 1. And that should be 0. Similarly, you can do I plus k. And that will be x plus z to be 0. Okay? So in fact, there will be multiple answers for this equation of this system of equation because you have 3 variables, but you only have 2 equations, right? And I'm actually not sure whether you guys have already taken the linear algebra course or not, and that is not really important for our course, but well, actually it is. We have to use some determinant. But anyway, to solve this, it is quite simple. You have a freedom of variable, right? You have 3 variables and 2 equations. So you can set things like this. Let me write it here. So this is always equal to, if you set x to be fixed, then y must be minus x, right? And z must also be minus x. So it is basically, there's basically this much solution. For any x, you can always plug this number inside that equation, and then you can get the correct solution. So that is for every x belongs to R. Okay. Okay, so now those are the solutions, but I have specified here that you're finding a unit vector, right? So let me um, try to help you understand this. We're finding a vector that is orthogonal to 2 vectors. So you see, if you have, okay, so you have 2 vectors on here, then this vector will be orthogonal to those 2 vectors, right? But there will be several of them, depending on the length, also direction, right? You can go this way and this way. So that's why there's a lot of choices for that. But for unit vector, there's actually only 2 choices because we want to fix the length. So it's either this way or this way. Now let us do that. I'm a little bit out of space. Let me try to move this. So let me move everything here. above. Okay. So you can do this by trying to compute the magnitude of the vector. So 1 squared plus minus 1 squared plus minus 1 squared taking square root is root 3, right? So the two possible solutions are plus minus root 3 minus. So don't forget that we are dividing the magnitude to make it normalized, right? We have done this last time. I should keep the notation consistent. So let's put minus here. Okay, those are the two possible solutions. And let me draw a picture to show how this means. So if that is I plus j, and that is I plus k, then you have two different choices. One is this way, v, possible choice, and one is this way. So technically, there will be infinitely many choices, but I ask you to fix the length, which is 1. So there's only two possible solutions, this way and this way. Okay, so that's exercise 27. And this example is not really important, but I mentioned this last time, so I want to cover it here. So it is one of the exercises in your textbook, and we also introduced this last time. So uh, I tell you guys that last time the magnitude plays nice with the scalar multiplication, which is c dot u taking magnitude is equal to c magnitude of u, right? However, there's no equality between vector addition. There's actually an inequality. And we will show now why the inequality is true. Okay. So first of all, I asked you to show why that u dot v is less or equal to, sorry, the absolute value. So be careful. This is the absolute value, not the magnitude, because u dot v is actually a number. So this number is less or equal to the product of their magnitude. And this is in fact quite direct. So let us recall what we have just done. What is u dot v? It is defined, it is derived to be u v cosine theta, right? However, these two guys are positive, so you can just break them out of the absolute value, correct? Like that. And you have cosine theta. But we already know that cosine theta is always between 0 and minus 1 and 1. So this is less or equal to whatever theta is, u dot v. Let's do that. Right? Is that clear? So that's a very simple proof about Cauchy structure inequality. It is named for some reason because there is more abstract version of this inequality. And this in this case, it is quite simple because you have a nice geometrical meaning, the cosine theta thing. Secondly, let's see how to prove this. So this is basically triangular inequality, right? If you have u, if you have v, this is u plus v. So the third side will always be less than the two side summing up. So geometrically, you have that. Now let this that prove it algebraically. So first of all, let us calculate the square of that because squaring is always better. That is u plus v taking dot product with u plus v, right? We have used this trick many times. Please try to memorize this because that is very, very useful. And now we apply our nice distributional property. You get square plus 2u dot v plus v squared, right? Now, this guy, whenever it is positive, negative, no matter what, the absolute value of this guy is always less than this guy, right? So that means that we always have this being less than u squared plus 2. Let me just copy this here. Plus v squared. Okay? And now the miracle happens. So this is a squared plus 2ab plus b squared, right? Which is simply a plus b squared. So you get u, let me write it better, plus v squared. Okay? So this guy is always less than this guy. And this guy, we use the continuous inequality. So let me mention here. Using what? Okay. And now since both of these are positive numbers, right? So you can just take square root. It is possible for a squared less than equal to b squared and give you a larger than b. For instance, if we take a to be minus 1, b to be minus 2, then 1 minus 1 squared, which is 1, is less than 4, which is minus 2 squared, right? However, a is larger than b. And that point, that reason is because a and b are negative. But whenever it is positive, you can very happily do your square root, and then you get our original triangular inequality. All right. So let me mention this. This is by taking square root. And the reason we can do that is that both of these are positive numbers, this guy and this guy. Okay. So you see that in this exercise, we sort of prove the nice Cauchy-Schwarz inequality, which is this guy, and then we prove the triangular inequality using the previous inequality. So this is not really important. I just want to mention this because we want completeness of the lecture. Okay, now let's proceed to our next important object, which is projection. So we are always considering how to project a vector on another vector, and we will see soon by example, which is the work done by a force. That is a more physical meaning. But now let us try to compute this. The projection of u onto another vector v is this guy. So let us go through the notation very carefully. This is a projection of u, so this is in the main component. We're projecting that vector on another vector v. So this is a projection of u onto v. Okay? They are not symmetrical, meaning that projection of u onto v is not necessarily equal to the projection of v onto u. So be careful with that. And this is given by u dot v, which is a scalar, divided by the magnitude of v squared multiplied by v. So this whole thing is a scalar, and this is a vector, okay? Let's sort of explain why I write it like this, because this is a scalar taking scalar multiplication with the vector v. Okay, so now being more precise, let us try to see what does a projection mean. So if you have a vector v and a vector u, then the projection of u is simply defined to be this guy. Okay, we project this perpendicularly, orthogonally, and then we write down the projection on v to be the projection of u on v, this notation. So you can see that if in particular u and v are orthogonal, then there's no projection because and anything project on v would just be 0. Lastly, if u and v have an obtuse angle, then you have a projection which is on the opposite direction of v. Okay, so that's basically what geometrically projection means. And now we'll prove it algebraically that this guy, defined geometrically, is indeed this formula. So to find a particular vector, there is 2 things to figure out. As I mentioned before, there's 2 information. One is the magnitude and one is the direction. So now let's first figure out direction. It's quite simple because you're projecting it on v, right? So it's either this direction or that direction. So it's either this direction or this direction. So it's plus minus v divided by its length. So don't forget, this is a unit vector, right? It is always of magnitude 1. And this guy represents the direction of v. For example, A times, oh, that's it. Don't you say, let's use V. So this guy will be 2 times the magnitude of the direction V. So like this, actually, if this is V, then this will be this guy, right? No, actually, no, sorry, my bad. If this is V, then what I just wrote out will be some vector in the direction of V, but the length is 2, right? V does not necessarily have length 1 or 2 or 3, but this guy always has length 1. So the new vector that I get here is a vector of magnitude 2. So the only thing we need to do is to figure out the magnitude of the projection vector, and I multiply that by this directional unit vector, and we get our projection, if that makes sense. So now what is the length of the magnitude, the length and magnitude of the projection vector? So if we see a diagram here, you see that it is basically listing times cosine data, right? Project down here. So it is the length of u, let me mention this first. So the length of the projection vector is defined to be the length of u project the cosine data onto v. But what is this? So let us recall, cosine data can actually be rewritten as u dot v divided by u v, right? And this guy cancels out with the numerator here. So you get u dot v divided by the magnitude of v, where you have an absolute value here because we're for now not considering directions. We're only considering the magnitude. Okay. Okay. Now the problem is that we have a plus minus here. We don't know whether it points towards v or opposite of v. Fortunately, u dot v tells you this. So let me go back here. Actually, this will be sufficient. So we know that whenever u and v have an obtuse angle, meaning that u dot v is negative, then the projection vector is in fact in the direction of opposite direction of v. And if they are of acute angle, then you have the projection of u actually have the same direction as v. So this guy actually has a signature that determines the direction of the projection of u. So fortunately, you can just write down this. This guy may or may not be negative, may or may not be positive. But anyway, the positive determines the direction of the same direction as v. The negative determines the negative direction, opposite direction as to v. So the magnitude multiplied by the directional vector, you get our formula, right? So this is a nice way to think about vectors. You always find the magnitude first, and you find direction, and then combine them together. You get your desired vector. In this case, very fortunately, the signature of u dot v determines the direction, whether it is opposite or not, of the projection vector. So anything, the thing that you have to take away is that the projection of u onto v is given by u dot v divided by the magnitude of v squared times the vector v. Okay, it's another vector, which is defined in this format. Okay, I would recommend you try to understand why this work, the proof work, because it sort of gives you a taste on how inner product, how dot product actually plays a role in geometry. Okay, now first let us try to do some example. So before that, since this is mentioned in textbook, so I think I should mention this also. Usually we simply call a quantity I just defined the vector projection. And this quantity here, which have a magnitude, which measures the magnitude of the projection vector, and also have a signature, tells you whether it is in direction of v or opposite. This magnitude is called a scalar projection. Okay, so in that case, whenever you're doing exercise in the textbook, you know what they mean. Vector projection is a vector, scalar projection is a scalar, and they are defined through these formulas. Okay, so first of all, I want you to find projection of u on v and v on u, right? So let us just go through the formulas. Projection of, I write v first, so let's write v, and u is given by u dot v divided by v squared, and that's in the direction of v. So what is u dot v? You get 2 times minus 3 plus 1 times 2, right? Let me write it carefully. Plus 1 times 2. What is v squared? It is minus squared plus 2 squared. And v is minus 3, 2, right? So for the quantity above, you get, what do you get? You get minus 6 plus 2, so that's minus 4. For the quantity below the denominator, you get 9 plus 4, so it's 13. Okay? And then we get 12 divided by 13 minus 8 divided by 13. That'll be the exact projection of u onto v. Similarly, with the exact same case, you have the projection of v onto u being, in fact, v dot u is equal to u dot v, so there's no point of writing it reversely, but I just want to follow the formula so you guys see that the notation is consistent. It will be in a direction of u. So, okay, let me just write this. This is the same. Minus 4 divided by u squared. So that's 2 squared plus 1 squared, which is 5. And you have 2 and 1. So that'll be minus 8 divided by 5 and minus 4 divided by 5. So you see that the projection of u on v and v on u is different. Okay? So be careful with that. Right. And for the rest of the two exercise, I try to present those because it's kind of geometrically important. It will not be really necessary for our calculus course, so you can just skip it. But be free to come back and see those example and anywhere, anytime. Sorry. So I want to show that V. So let me mention that this is perpendicular or orthogonal. If you ever see left some notation that I'm not defining, please let me know. This is orthogonal. So I want to show that V is perpendicular or orthogonal to U minus projection of U on V. So first of all, that is geometrically true because you see that, okay, in this case, what is U minus projection of U on V? It is this guy, right? And this guy is obviously perpendicular or orthogonal to V. Similarly, for this guy, this is orthogonal to V, right? For this guy, it is quite natural because U is simply, the projection is simply 0. So U minus projection of U is simply U. And it is basically orthogonal to V, right? So geometrically, it should be true. Now let's verify algebraically by every ingredient that we have. So first of all, let's recall what is orthogonal. Orthogonality can be deduced from dot product, right? Whenever dot product is 0, you get orthogonality. So that's what we want to do. We want to show, let me write it in blue. Want to show that they have dot product being 0. Like that. And it's a scalar, not a number, not a vector, sorry. So let us just compute that directly. So what is V dot this guy? By distributional law, you have V dot U, right? And V dot the whole thing here. But that is given by the formula of U dot V divided by V squared, right? And then you have V here. Don't forget, this guy is a scalar. So this scalar is inconsequential of the dot product. So this is simply V dot V multiplied by this scalar. Let me just repeat everything here. And what I want to write down is something like this. And I want to take a bracket out. Now, what is v dot v? V dot v is actually just v squared, right? Just for a reference, what did I just do here? This is u dot av equal to a u dot v, right? So I have used our law here, which is again very, very easy to verify. But the point is to understand how it actually works. So this guy is actually a constant. Put that constant outside, you get the actual dot product, and everything is just numbers. So this is this guy, and miraculously, this two guy cancels out, and you get u dot v, v dot u minus u dot v, and those are the same thing because the dot product commutes. So it's 0. And then we're done, right? Because orthogonality comes from the dot product being 0. And just to remind, this is completely intuitive due to the fact that u minus the projection is simply this guy, or this guy, or this guy. And those are basically orthogonal to v, right? So this is just verifying something that we geometrically know, and we can verify algebraically. Okay, so there's that. Now, again, as I mentioned, this is not a crucial example, but it's a very, very useful formula in geometry. So this example is telling you how do you compute a distance throughout a point to a line. So let us first define how that geometrically picture a distance. If you have a line given here, which is ax plus, actually, let me draw it larger because I want to prove it. Let me draw it here. So this is ax plus by plus c equal to 0. And here you get some point p x naught y naught. Okay. This thing actually also works in two-dimensional thing, but I'll just first present the two-dimensional object. So distance is basically, if you draw an orthogonal line here, then this is what we are looking. So let me make that indentation to make things more compact. If this thing is called a line L, then let me just call this distance the distance between L and P. Okay, actually P and L will be better. The point to the line. Okay. Now, how do I do this, and why do I introduce this in this section? Because we can actually derive that by projectional formula. So first of all, let us find any point here. Any point will suffice. Let us do maybe just 0. When x is 0, then b will be minus c over b, right? If you can see that. 0, when you're 0 here, then y must be minus c over b, right? Then what do I do? Now, the interesting part is coming. If I connect this thing, I get a vector, right? So this thing. Let me write down this to be u. Okay, so the vector u can be computed by p subtract by this point, right? And if I project it onto this orthogonal vector, then I will get this vector, right? And this vector is exactly what we want if we compute the length, right? Okay, I hope that all makes sense. So how do we project the vector? We have to first understand what is this vector, right? And I believe I guess that this might be in your junior high or high school textbook, or maybe in your first year calculus or pre-algebra or something. But anyway, given a line here, we always have the directional vector and the normal vector given in this format. And I guess we will be talking about this in section 5, which we're introducing plane and lines. But let me first foreshadow something here. So the directional vector, let me put this here and then go down here. Okay. So the directional vector, which is a vector in the direction of a line, is in fact given by minus b minus b. Okay. You can do plus minus. You can do b plus minus a. B minus a. Sorry, that's the same thing. You can do b minus a because I'm not specifying this way or this way. Okay, so there's infinite line choice, but it is in this direction. Everything is parallel to this direction. And the normal vector, this is called normal vector. We'll be talking about this more afterwards, but again, just foreshadowing. It's actually given directly by its coefficient AB. So A and B here. You can sort of see it through the definition of this equation because whenever we have another point here, x naught, y naught, okay, sorry, x1, y1, say, okay, then x1, y1 satisfies this equation, right? So ax1, yeah, let me just do it here. So you have 2 points, x1, y1, and x2, y2. Those two satisfy the equation. So you have x1 y1 plus c is equal to 0. Ax2 plus by2 plus c is equal to 0, right? Now, if you subtract those, you get a x1 minus x2 plus b y1 minus y2 being 0. And what is that? That is ab taking dot product with x1 minus x2, y1 minus y2, right? Now, what is the vector here? It is actually this direction, right? So that is a directional vector of the line. It is parallel to the direction of the line, right? So what happens when this thing taking dot product with this guy is 0? That means that AB is the normal vector, right? That's what we are given here. Okay, so this is in direction of AB. Of course, you can multiply different scalars, but AB will be a good representation. And actually, for every different choice of that normal vector, say AB, say 2A, 2B, say minus 3A, minus 3B, you always get the same projection because the only thing that we care about is this line. Either you project on this thing, you project on this thing, you project on this thing, you always get the same thing, which is this small thing here. Okay, so basically the option now is to project this thing on that guy. So first of all, the projection, oh, let me use black, sorry, to be consistent. So the projection of AB, U1 AB, we want to compute the length, right? The length will be the distance. Okay, so let me make it more compact. dPL, the distance, will be the magnitude of this projection. Don't forget, this is the projection. This is the green line. Okay. And let me just mention that I will use this color. Let me use this color. So this, okay, there's too many things going on here. This thing. This will be the projection of AB. Actually, it is not clear whether it is this way or this way. It depends on how your AB is, but it is, let me write plus minus. Okay. It might be this way. Depends on how AB looks like. But yeah, anyway, the only thing we care about is the length. So you get, let me go back here. We have seen that the length is given by this formula, right? So basically, it is U dot AB taking absolute value divided by the length of AB squared. Now, what is U? U is given to be P minus this guy, right? So X naught minus 0, Y naught minus C divided by B, taking dot product with AB. And what is the denominator? The denominator is actually just A squared plus B squared, right? Sorry, I shouldn't put a square here. There's no square. So if you recall here, there's no square. So there's actually a square root here. And eventually you can see that very nicely. It is actually 8x naught plus by naught minus c. Oh, it should be plus c, sorry, because we are subtracting minus c over b. So it's plus c. That's where I feel kind of strange. Okay. Okay. So surprisingly, the distance is actually very easy to calculate it. If you have a point P, let me actually put it above here. If you have a point P and you have a line L, then to compute the distance, basically plug the x naught and y naught inside that equation and divide by a squared plus b squared taking square root. So for example, if that x naught y naught actually belongs to a line, then distance is 0, right? And it actually holds because if you plug it in, it is 0, then you get distance 0. So it is very consistent to some degree. Okay, so this is a very, very nice formula. It is very universal. And let us try to plug that in some example. So this is for problem 1. Problem 2, so d PL will be, again, just plug the number inside the equation. 2 times 2 minus 3 times 1 plus 4, taking absolute value, divided by a squared plus b squared. Okay, and then we're done. So the numerator is 4 minus 3, that's 1, so it's 5, divided by square root of 13. Right? So that's a really nice formula about projections. If you want to find the distance of a point and a line, then we can do that. And actually, you can do the exact same thing for a point and a plane, which we will be coming back in section 5, 12.5, okay? So that's a good example. For next example, I want to do some physics thingy. So this is from exercise 51. So it's that a slide pull along a level path through snow by a rope. So that is something like this. You have a sled. So this is a sled. And it's pulled through the snow by a rope. So this is the rope. And it is acting of 30 pounds, sorry. And it is acting of an angle 40 degrees. So let me do this here. Okay. And this angle is 40 degrees. Okay. And we have moved it horizontally for how much? For 80 feet. Okay. So let me write down this. This is F, the force, and this is called D, the displacement. Displacement. And this is called force. Okay. And we know that in physics, is it a physics formula? Let me write down here. So work is actually equal to how much force you actually apply to this displacement. So that is a projection. So that is the force is a vector taking dot product with displacement. Displacement. Okay. So work is a scalar and force and displacements are vectors. They are of some direction, but work is only of a quantity. So that is calculating how much energy you're actually given the sled over this displacements. Okay. So the work actually not really energy. It'll be a frequency, but yeah, let's don't go too deep about the physical meaning. I just want to display some application of the dot product. So in our calculation, the work will simply be, we can apply it through our formula, right? Actually, let me first write down this. F dot D. And that is F W, oh, D, my bad. D and the cosine angle. So they are of this angle of difference, right? So that's 40. So basically we're trying to calculate 30 times 80 times cosine 40, right? And let me do the algebra here. 30, 80, cosine 40. So it's 1838.5. And we are multiplying pound toward feet. So that'll be our unit, okay? That's how much work you have done. Right. So having going through these examples, let us quickly review what we have done. So we are defining dot product in this lecture, and we have introduced several properties of the dot product. So first of all, the algebraic definition of dot product is simply multiplying each entry together and then add those three things up, or two things, depending on what dimension. And there are several properties, but the most important one is that if you take dot product between V and V, you get the square root of the magnitude of V. And this is a very, very important formula. For a geometrical interpretation of the dot product, we're simply calculating the product of the length of U, length of V, and cosine theta, where theta is the angle between U and V. In that formula, you can convert it into this nice formula that calculates the angle. So cosine of the angle between those vectors will always be U dot V divided by their length taken product. And so under the interpretation of this formula, you see that whenever U dot V is positive, you always get a acute angle. When it is zero, you get orthogonal. And this is of most important. And when U dot V is negative, you get obtuse angle. So you can solve any equation regarding two vector being perpendicular or orthogonal. In this case, we want to find a unit vector that is orthogonal to two vectors, and we actually find out there's only two of them. And we prove several inequality. Those are not really important and not really matters in our course. And this important theorem. So the projection of a vector on another vector is given by this really nice formula, which you can separate into different components. The first component is the magnitude. The second one is the direction. Okay. And again, you can see that whenever U and V, U dot V is positive, then they share the same direction. When U dot V is negative, they share the opposite direction. When U dot V is zero, it is orthogonal. So there's nothing to worry about. The projection is simply zero. We have done some examples on U on V and V on U. And we have shown that naturally V will be perpendicular to the vector given by U minus its projection because it simply looks like this, this, and this, right? And then we show a really pretty formula about projection on the plane or on a line, sorry. And we find out the distance between a point and a line given by this very decent formula. Let me specify here. And lastly, we see that how work is defined. Work is defined to be the dot product between force and displacement. It is a scalar. And we calculated an example from our textbook. W is equal to F dot D. And the total work that the force has done on the sled is 1838.5 pound-feet. Right. So that'll be all. And I know that this lecture might be more conceptual and there's more theorem formula in this lecture in comparison to the previous two. So be prepared. We will be doing this a lot more in the next one and in the next one and throughout our whole semester. So yeah, I hope to see you guys in the next video. See you.